So I want to start today with essentially finishing last time. I wanted to show you all the fancy and fun Fibonacci stuff. So some of these we were able to actually talk about last time. For example, the bee family tree. And you saw how basically out of the rule of how bees reproduce, we got a Fibonacci sequence. Okay. So I'm going to show you some other things as well. Pine cones. So pine cones, you can find the Fibonacci sequence in the little, I don't know, ridges. Yeah, I forget what they're called. Okay. And you can find them in the spirals of the ridges. Now what's very cool is that you can find them in two different ways. You look at the spiral. Now it depends. Now the way that the little ridges are arranged, you can spiral in one of two directions. You can either spiral clockwise or counterclockwise, counting out from the very tip. And what you can see in the picture illustrated here is that if you count out the spiral from the center in one direction, you get let's see, you get one Fibonacci number. Or I should say rather and if you count it, but if you look at it in the counterclockwise direction, you get the next consecutive Fibonacci number. So what's illustrated here is that we have, I know the numbers are very small, but what we have here is 8 and 13. So, and the lines have been added in to help you see what's going on. Seriously or kidding? Okay. In the first picture, do you see the spiral lines? Okay. So there are let's see. I guess there are 8 of these spiral lines. Is one way to see it. Another way to think of this is that if you were to spiral out, you would count one layer at a time. So we go here. First on the first line, then on the next line, then on the next line, then on the next line. So if you were to spiral out, so there, if you look clockwise, you'll see 8 spirals coming out. But if you were to spiral out counterclockwise, you would hop through each spiral one at a time. So there would be 8 cones in that spiral. 8 ridges in that spiral. Vice versa for the other way. There are, if you look at counterclockwise, first of all, does everyone see how you can identify spirals that both spiral out clockwise and counterclockwise? Just because of the sort of quasi-diagonal way that the ridges are arranged. Okay. So if you were to look at the way the ridges spiral counterclockwise, you'd see, counting from the center, that there are 13 of them. That's what the lines represent. But once you know that, you can see that if you were to spiral out clockwise, then you would cut through each one of those spirals one time as you made your clockwise spiral. So that if you go clockwise, each spiral is going to cross each of these lines once. It's going to have 13 ridges. And then of course 8 and 13 are consecutive Fibonacci numbers. Okay. So does that make a bit of sense? All right. So now that we've so pine cones are one of the sort of famous examples of Fibonacci numbers in nature. And now that you understand the basic pattern of spirals both clockwise and counterclockwise, let's look at some more cool pictures. Okay. So it turns out that lots and lots and lots and lots of flowers have Fibonacci numbers in them. And here are just a couple of examples. Now, as we just saw from the previous example, the way to identify the Fibonacci numbers, well, one way is if you look at, let's see, either the seeds or the petals. So in the first two, I'm interested in seeds, or what constitute the seeds in the middle. And if you're able to, and of course I know the first two are kind of densely packed, so it's probably hard to count on this picture. However, science tells us that the first one has spirals of 13 and 21, if you're able to get in there and count them. And the second one has spirals of 8 and 13, if you go clockwise and counterclockwise. So, short of counting them, you just have to take my word for it. And the third flower, and again, you can see the little seeds get so small in the middle, but the third flower has spirals of 21 and 34, if you go clockwise and counterclockwise. And then the last flower, well, that one's got petals, so it's a bit easy. That one, we're talking about the petals, so it's a bit easier to count. That one's got spirals of 3 and 5. That one's got nice big petals, so it's very pretty. Yeah, botanists typically. Yeah. Botanists are the people who study botany, which is plants. So yeah, of course. I mean, botanists study everything that there is to know about plants, so they categorize everything. And then, I don't know exactly how it happened, but one day a mathematician just happened to be walking by and said, hey, wait, I know those numbers. Okay. And here are some nice ones as well. Sorry? The first two have fancy Latin names. The fourth one, it begins with an A and it's escaping me right now. Yeah, I don't remember, but I'll let you know next time. The name's escaping me right now. The last two, I'll certainly tell you that. Those are sunflowers. The bottom two right here. So these, if you were to count, you'd get Fibonacci numbers. I don't know what they are, but you can see that if there are even more seeds and they're even more densely packed, you actually get what just looks like a very pretty spiral pattern in general. Yeah. Okay. Okay. So we've talked about the seeds in the middle. We can also talk about the petals. And a lot of flowers, the petals on the outside, they have a Fibonacci number of petals. So I can tell you because I remember the let me see. If I remember correctly, the purple one, the first one is aster. Actually, I think they might. I think these are actually. This is two different varieties of aster.
Isn't that the big
Well, just the petals. You can count the petals. On the purple one or the light purple one, there are 8 petals. Right. What about on the indigo one, the next one? 13. 13. So Fibonacci numbers and Fibonacci sequences appear all over the place in nature. These are just some of the sort of more vibrant examples. Also, yeah, question. Any, sorry? Actually, that's a good question. If you for the human body, if you just look at sort of like the major elements of it, we've really only got like 1 or 2 of anything. So it's not like we have, you know, like 13 fingers and 21 toes or anything like that, you know. So the numbers don't get big enough to produce Fibonacci numbers. So there are. It's actually interesting because there aren't any that I know of. I think that the system, you do get some very, very interesting patterns, but I think that as far as I know, you get really complicated looking things, and because they're so complex, they're too complex to be arranged in a Fibonacci kind of, or to be numbered or to be arranged in a Fibonacci kind of way. Yeah. There's no part of the body that comes to the mind off the top of my head that's as simple as, for example, arranging seeds or sprouting petals. I mean, yeah, we sprout arms. Okay, so oh my God, we have 5 extremities. We've got a head and 2 arms and 2 legs. So if you like, we got 5 extremities. That's a Fibonacci number. I don't know if that's terribly coincidental or just because the numbers are so small, almost everything's a Fibonacci number. Yeah. Once the numbers get big in the human body, the systems are really complex. Too much so to be Fibonacci. Okay. Next. Where does the golden ratio appear? Alright. Well, this one we talked about last time. In the human body, the ideal is the golden ratio is the ideal ratio of total height to navel height. And there is the human ideal. Okay. Also, I mentioned you can find the golden ratio in a pentagram. So if you'll recall, the golden ratio, well, it's all over the place. It's the ratio of this side to this side. It's also the ratio of, let's see, I want to get this right, this side to this side. So all those sorts of ratios are golden ratios. Yeah, pentagram. Alright. So other sort of more interesting artistic cultural examples. Stradivarius Violin. Now, I'm not a classical musician, but I've heard of the Stradivarius Violin. They're made by the violin maker Stradivarius, who was active, I think, in the 18th century, 17th or 18th century, and there are very few left, and they're quite famous for their beautiful musical properties and also unbelievably expensive. Well, it turns out that the violin is in Fibonacci proportions. Next, the Mona Lisa. The Mona Lisa has got all kinds of Fibonacci proportions in it. Now I hope you can see it. Can you see those thin white lines? Oh, okay. So those aren't part of the original painting. No one defaced the painting. This is to point out what's marked off is where the hand is, where the lip of the dress is, where the chin is, where the nose is, where the eyes or eyebrows are, and where her hairline is. If you take those ratios, for example, the distance from the hand to the lip to the cusp of the dress, and then from the dress to the chin, that's a golden ratio. Yeah. So all the different ratios that are indicated by the white lines, those are all golden ratios. A lot of the compositional aspects of the Mona Lisa have the golden ratio. And because of Da Vinci's work in mathematics and his familiarity with a lot of the math, people believe that this is actually done on purpose. Okay. The Parthenon. Okay. So just to remind, so here's a picture of the Parthenon as it stands today. Of course, it's a little nicer back then. As I said last time, the Parthenon was designed by Phidias to celebrate Pericles saving Athens during the Trojan War in the 5th century BC. Phidias is Greek, so the first letter in his name is Phi, and that letter is often used to denote the golden ratio. Okay. What does the golden ratio have to do with this pile of rock? There you go. those rectangles give a scheme to the building, and every ratio that you see is a golden ratio. So, Parthenon is historically significant. It's architecturally significant. So it's probably one of the most famous ruins in probably definitely the Western world, maybe the entire world. And it's got golden ratio everywhere. And of course, this is from 5th century BC, so people wonder to this day if this was done on purpose or just because it looked pretty. Could be. Okay. All right. Here's another golden ratio that looks really pretty. The Cathedral of Shaft. And this is from 13th century France. So there we go. So you can really, this actually is a great example because you can really see the golden ratio here. Because remember how we said the golden ratio was defined. We said the golden ratio is such that you take a rectangle and then things are in the golden ratio if you can chop off a square and the rectangle that remains is in the same proportion. Well, in this case, the square is perfectly defined by the part of the rectangle that encloses the circle. So if you chop that off, what's left is another rectangle that's got golden ratio proportions. And it's very pretty. And last bit of culture. This is the Unité d'Habitation, designed by Le Corbusier, who is a very famous 20th century architect, and this is in France. All right. Now, can anyone owe anyone see the golden ratio in this building? So remember what I just said about how the golden ratio is defined. If you take a rectangle,
The left side to the right side.
yeah, exactly. Take a rectangle, and if you can chop off a square and have a rectangle that's still in the same proportions as the original rectangle, then that's the golden ratio. Now, Le Corbusier, as you might be able to guess because it's so obvious, he actually designed his building using the golden ratio completely intentionally. So he actually, you can see that strip down not quite the middle of the building. He did that on purpose. He did that to highlight the inclusion of the golden ratio into his design. Okay. So what else do we have? So that's all stuff we did. Okay. So the last bit, and there may or may not have been one homework question. Okay. May or may not have been one homework question related to this, I don't remember. But last thing I didn't get to, what is the sum? We talked about what is the sum of the first n Fibonacci numbers, and it worked out really, really nicely and easily. We can also ask this: what is the sum of the squares of the first n Fibonacci numbers? So 1 squared plus 1 squared plus 2 squared plus 3 squared, all the way up to fn squared. Now you might say, well, that seems very hard. There's no way I could possibly understand or figure out what's going on. Turns out that you can answer this question of what the sum is by using an unbelievably clever picture. So remember when problem solving we said, hey, let's look at this picture and use the picture to answer the question. Well, what does this picture show? It's not just the Fibonacci numbers. What is it? Okay. How can we represent 1 squared? Yes, but how can you represent it as a picture? You draw a square, exactly. Now how can you the next one is 1 squared, so that would be another square. Now how can you represent 2 squared? Yeah. Yeah. We've already got a side of length 2. We've already got a side of length 2, so you just need to square it. Now what's next? What comes after 2 squared? 3 squared. Now where are we going to put that square? Where are we going to put that 3 by 3 square? We've already got a side of length 3. It's right there. 3 by 3. And the next one is 5 squared. Yeah. Now I'd have put it on top to show that it is 2 plus 3. But if you put it up here, or if you put it down here, it's the same thing. Oops. So you can see that, again, this diagram just represents 1 squared plus 1 squared plus 2 squared, blah, blah, blah. We actually don't need this part. Right. Except to show us that when you add up through 13 squared, again, remember the biggest square here is this one, which is 13 squared. So this represents 1 squared up through 13 squared. It equals what? Well, what it gives you is this rectangle. Now, how big is that rectangle? What are the dimensions of the rectangle? Let's see. Okay. How tall is the rectangle? 13. No, how tall is it? Check it. It's not 13. The square is 13. So how much is the whole? Yeah, exactly. It's 21. And how wide is the rectangle? It's the width is just the square, so it's 13. So there you go. So if you add up all the squares, so another way to write this out is that f1 squared plus blah 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 up to fn squared equals, and actually to make this prettier, instead I'm just going to write 13 times 21. So if you add up f1 squared through fn squared, what's the result? Well, if we go 1 squared up through 13 squared, we get 13 times 21. So if we start at f1 and go up to fn, what's going to be the general formula? There's no square there. What is 13? Right, or in general. So actually you're quite right. What I should do, oops, okay. I think there's probably a middle step that I can include in here to make this a little more clear. So 13 is 1, 2, 3, 4, 5, 6. You're right. So what we said so far is that f1 squared through f7 squared equals what? What is 13 in terms of Fibonacci? It's f7. And what is 21? It's f8. So now let's say this in general. This is if we take the sum of the first 7 Fibonacci squares. So, but now let's say in general what this is. In general, f1 squared up through fn squared is going to be what? there you go. And good job figuring it out. And that's a pretty extraordinary relationship. Surprising that it's so simple. Yeah. So this picture is very clever. Okay.